come to our scientific programme now, and it's a great pleasure to invite Professor Steven Smartt from Queen's University Belfast to give the George Darwin lecture on Kilonovae and the birth of multi-messenger astronomy.
So thank you. It's a pleasure and an honour to give the George Darwin lecture this year for two reasons. One, just the honour of giving this lecture at the Royal Astronomical Society, but also to have been part of this breakthrough discovery last year that many of you will have heard of, where for the first time we combined the detection of gravitational waves with identifying the source directly in electromagnetic radiation. Last year, when the news broke, there were over 70 papers released in the first day, announcing the discovery of this neutron star merger and the discovery of electromagnetic radiation. So I'll give you a summary of what of the highlights of this discovery and what me and my group did for this. I'll cover mostly what has been the discovery from the aspect of what we call kilonovae, and those are transient objects which look like supernovae but are dimmer. And the reason they get their name is that they're 1,000 times brighter than novae. There's another part of this story which deals with the high energy aspect of the gamma rays, the X-ray, and the radio detections, which I won't go into in detail because it would take me too long. So I'm going to focus mostly on what caused this this event that we call a kilonova. I know this audience is very broad. I see some experts in the audience, and I know there are some people here from a general background. So I'm going to try and reach out to both of you. I'll give some details on the technical aspect, but I'll try and give an overview of why this discovery was so important and the interest in terms of general physics and general science. Let me remind you of the universe's densest objects. And so these are the objects that potentially can create gravitational waves. White dwarfs, neutron stars, and black holes. So these are the leftover remnants of stars of different masses. White dwarfs come from stars like the sun. Our own sun will lose its hydrogen envelope and it will create a white dwarf at the end of its lifetime. Let me give you the density of these objects just to put them in perspective. And I'm going to start with a very non-SI unit, and that's grams per centimeter cubed. And the reason I'll give that is that it's what is you can enclose on a teaspoon. So white dwarfs are objects that are about the radius of the Earth, so about 6,000 kilometers. They've got masses up to 1.4 times the mass of the Sun. Typical mass is about 0.7, or the median mass in our galaxy. So the density of those is 10 to the 4 grams per centimeter cubed. Neutron stars, those are objects which again are about 1.4 times the mass of the Sun, up to about 2 times the mass of the Sun. That's the maximum mass that we know of in our galaxy, and those have radii of 10 kilometers. So those are the leftover remnants of more massive stars greater than about 8 times the mass of the Sun, and those occur when the core of the star burns its nuclear fuel all the way to iron. It can't support itself anymore. The iron core collapses, forms a neutron star, and that iron core, just before it collapses, is about the size of the Earth and is like an iron white dwarf, but that collapses down to 10 kilometers in radius. And the release of that gravitational potential energy is what drives a supernova explosion. So these are incredibly dense. These are up to 10 to the 11 kilograms per centimeter cubed, and the way I like to describe that to general audiences is squeeze all of humanity onto a teaspoon, and that's the density of neutron star material. And black holes, of course, are objects which are even denser than neutron stars. So these have masses greater than two solar masses. There does seem to be a mass gap between the most massive neutron star we know in the galaxy and the least massive black hole. And so the least massive black hole is around 5 solar masses, as we'll see in a second. And those have typical radii of about 5 kilometers, or greater than 5 kilometers in radius. The radius is given by this formula for the Schwarzschild radius, the simple idea of the event horizon. So those are the universe's densest objects, and the reason that they are important is that Einstein predicted over a century ago that gravitational waves might be produced if you have massive accelerating objects. And those three types of objects white dwarfs, neutron stars, and black holes, we know are in binary systems. We know that they exist. Those binary systems exist in our own galaxy. So therefore, the objects are accelerating, and accelerating masses have the potential to produce gravitational waves. So from a simple point of view, gravitational wave is a distortion in space and time. So on the right, you see the two massive objects, in this case, two neutron stars merging. And this is on the right-hand side, you see the matter being traced. On the left-hand side, you see the matter being traced. On the right-hand side, this is a visualization of the gravitational waves that these two massive objects produce. Because they're accelerating and they're massive enough, these produce gravitational waves that have an amplitude that on Earth is potentially detectable. So I'm going to show you a few equations here for the more technically minded, to show you the strength of the typical strength of gravitational waves and what measurements we have to make on Earth to detect them. As many of you know, I'm not part of the LIGO-Virgo consortium, but let me pull out some of the interesting, fairly simple physics that they highlight in terms of explaining how they detect gravitational waves. So for electromagnetic radiation, the lowest multipole as possible, of course, is dipole radiation. For gravitational wave radiation, because there's no polarity, we need a quadrupole moment, which means we need a massive, an asymmetric system in which that mass is accelerated. And the strength of that, the key thing, the thing that Einstein predicted and then the theorists behind the LIGO-Virgo collaboration predicted, was that the strength of that amplitude, the strength of the gravitational wave, we call the strain, and you'll see this letter H appear. And we can approximate, so the general theory of relativity predicts that the strain, the strength of a gravitational wave is given by, to first order, is given by this formula. So if we have two objects in a binary system and they're both of mass m here, and they have an angular frequency of omega, they're separated by r and they're at distance small r, then the strength of that gravitational wave source is given to first order in a reasonable approximation by this. Now, if you just assume a Newtonian orbit, that the two masses are equal mass orbiting around each other, approximately the angular frequency will be given by this, which means we can remove the omega term in that, which gives us this value for h, 10 to the minus 21, which I'll come back to. So we get this 10 to the minus 21 because if we put in typical masses for neutron stars or black holes, and we put in typical distances to nearby galaxies, that h comes out as 10 to the minus 21. So this is the characteristic strength of a gravitational wave. And it's dimensionless, of course. So this is what has been predicted now was predicted for over a century, that if you want to detect gravitational waves and you want to detect distortions in space, you need to get to the level of measuring distances to 10 to the minus 21. That's the characteristic strength of the wave. So this is what the LIGO and Virgo experiments set out to do. And they started off doing this in the 80s, and it wasn't until they made the jump to their advanced technology that it became possible to get to that level of accuracy. So these are the two images of the two experiments. LIGO in Livingston in the US. So in the US there are two detectors, LIGO Livingston and LIGO Hanford, and they're separated by the size of the US continent. And then there's another experiment in Virgo, which is very similar to the two LIGO detectors. There's a working experiment in Germany called GEO 600, but it doesn't quite have the sensitivity of these three. There's an experiment in Japan called Kagra, which is currently under construction, which is a different design concept. It's underground, it's cryogenic. It remains to be seen exactly how they will compare in sensitivity to the three working detectors. And there is a future plan to put a copy of LIGO in India. But as of last year, and I'll talk about the three working detectors, the two LIGO detectors in the US and Virgo in Italy. So these are, as you can see here, they have a base station and then they have two arms which are at right angles. And the basic experiment is to measure distances along these two arms at right angles. So this is what LIGO does. It has a laser in this base station. It shoots a laser beam up up both arms. It uses a beam splitter here. So the laser comes in, the beam is split. It's shot up these two arms, which are each approximately 4 kilometers in length. And the laser bounces back and forth between these test masses. And the basic idea here is just to measure the distance x and y. So when a gravitational wave passes and the strength is strongest, the detectable strength is strongest, is when the gravitational wave is perpendicular to the detector. This distance y and the distance x change. So what the experiment does, and this is really all it does, is measure those two distances to extremely high accuracy. At 4 kilometers distance, if you want to get to the strength of the gravitational wave, which is 10 to the minus 21, it means you need to measure this distance between the two test masses to 0.002 of a proton. So that is basically LIGO's experiment, to measure two distances to this accuracy. And when a gravitational wave passes, then this arm, for example, gets shorter and this arm gets longer at the same time. And so that's LIGO's basic measurement and capability. But it's amazing how much information they can extract just from those two measurements, as we'll see. So these are the data from the first discovery of gravitational waves in 2015. This is the waveform detected in Washington, in Hanford, and this is the one detected in Livingston. So you can see that these are almost identical waveforms. Not quite, because they're offset by approximately the speed of light times the distance between the two detectors. And what was plotted here is time versus strain. So this is this value of h in units of 10 to the minus 21, which I pointed out before. So you can see that the characteristic strength of the wave as it comes in here is around a bit more than 10 to the minus 21. And you can see in both cases here that the same signal is detected. Have a look at this. This is 0.3 to 0.5. The whole signal lasts 0.1 of a second for this particular event. And the same signal, of course, was detected in both. So this shows you the frequency versus time. What you can measure here is you can measure the amplitude of the wave. You can measure the frequency, of course, and you can also measure the frequency derivative. So you can see that the frequency is getting higher. This shows the frequency here. So this is 32 hertz. So that 32 times per second. This directly traces what we're seeing here is binary black holes orbiting around each other. That's the frequency of their orbit. Actually differs by a factor of 2, but the first order, that's 32 times per second. They orbit each other. They get closer and closer. They end up orbiting each other at 250 times per second, and then they merge. So that was the interpretation of this signal back in 2015. And this was the paper that discovered gravitational waves. So an unmistakable signature. It actually happened during their engineering run, took them completely by surprise, the strength of the signature in both detectors and the fact that this was unambiguous. So this was the discovery that led to the Nobel Prize for Rainer Weiss, Kip Thorne, and Barry Barish. They estimated that the two objects that produced this signal, you can estimate the mass of the objects from the amplitude of the signal, combined with their the frequency. And they estimated that the two objects were of order about 30 solar masses for each. These were the most massive black holes known, most massive stellar mass black holes known, which I'll show in a second. And this shows you their separation. They're of order as they come closer together. Sorry, the black ones, the separation as they come closer to their Schwarzschild radius, and their velocities approach 0.6 the speed of light as they merge. I once saw a TV program with Kip Thorne on it, who said, and at the time we were all sworn to secrecy in 2015, so my group and others had signed an agreement with LIGO that they would give us the sky maps of where they thought these objects were in the sky. We weren't allowed to tell anyone else. We had to, if we found something unusual in electromagnetic radiation, then we had to go back and tell LIGO and then discuss how we might announce it. But we had to keep it all confidential. And Kip Thorne was on the TV and he said, I wasn't even allowed to tell my wife. So I don't believe him, because if I'd have made a discovery like this and I walk through the door, my wife's here, so she can she can confirm this. If I walk through the door, I'd have looked pretty happy with myself. I looked pretty pleased with myself, and if she had said, "So what's up?" and I'd said nothing. It was all fine after that. So she'd have known I was lying, and then I had to continue lying, and then that wouldn't have been good. So I'm not sure Kip Thorne was actually telling the truth there. So after the discovery that I'll talk about, and when we discovered an electromagnetic radiation, I definitely told my wife. I didn't listen to anything that LIGO told me. So it was either divorce from LIGO or divorce from my wife. There's only one winner there, I think. So you can ask Kip Thorne about that if you see him. During the first two LIGO runs, up until August last year, LIGO discovered 5 binary black hole systems. These were the most massive stellar mass black hole systems known. And of course, the reason we think that they discovered those first is that they are the loudest. They're the loudest signature in gravitational waves because of the large masses. It was a surprise that we found black holes of this mass. So this diagram shows you there's nothing meaningful in the x-axis here. It's just a scatter plot. This is the mass of the object in terms of the sun's mass. So solar mass is here. Neutron stars are all down here. These are the masses of neutron stars known in our galaxy, mostly from binary systems. I think all from binary systems. And the purple dots here are objects in our galaxy, which again are in binary systems, and these are estimated masses for these objects, which are significantly above neutron stars, and therefore we think they are black holes. And then the blue objects are LIGO's detections of black holes. So the individual black holes are shown here, and then they merge and give these large objects here, which are objects up to about, so these merging objects of 20 to 30 solar masses then produce black holes, which are up at 50 to 60 solar masses. So we certainly know these binary black holes black holes exist in binary systems of these masses in the universe, and they produce very large black holes of around 50 to 60 solar masses. So this was the situation as of 14th of August 2017 last year. And so the question then, after these had been discovered, the question for us electromagnetic astronomers is that where in the sky did they appear? Could we locate them in electromagnetic radiation, and could we find their host galaxies? And that finding those would open up then a whole new area of physics and astrophysics to uncover. So this is a difficult problem, particularly just with the 2 working detectors in LIGO, which were Virgo didn't come online scientifically and wasn't able to approach the LIGO sensitivity until end of July, August last year. So before that, we had only 2 detectors observing the sky. So these produced quite coarse and large areas of the sky, which gave the location of the gravitational wave. And these areas here show you. So let's take this one for example. So the gravitational wave detected in January last year. The red area shows how they've restricted the area in the sky just from the 2 LIGO detectors. And this is really just from the time difference between the detection of the waves in the 2 LIGO detectors separated by across the US continent. So it's just the time delay really gives a ring on the sky. But the size of these are enormous, so around 1,000 square degrees. And this means that finding anything in those areas is quite difficult. So what we had been doing in the first 2 runs of LIGO Virgo is mapping out parts of these with our wide field telescopes. So telescopes in Hawaii and Chile in particular had been trying to map out these regions. And because these are binary black hole systems, we didn't really know what we were looking for. So we had 2 problems. One is that it's a very large sky area, and the other problem is we didn't really know what we expected to see with merging black holes. But we tried this over the first 2 runs, and we didn't discover anything that might be related to the sources. However, this changed. The capability of the gravitational wave experiments changed last July, and when Virgo came online, then that 3rd detector breaks the degeneracy between the 2 in the US and gives a much smaller sky localization map to try and locate the object in electromagnetic radiation. So in August last year, on the 14th of August last year, LIGO and Virgo jointly detected for the first time gravitational waves in all 3 detectors. So this was another binary black hole system. So again, this whole signal lasted about 0.15 of a second or so. This shows you the Virgo data, noisier than the other two, but still quite convincing that there is a modulated signal here with the same frequency and the same frequency derivative as the two US detectors. And you can pick it out here in the frequency time diagram. So this was fantastic last year in August. We all got very excited, and this shows you from our perspective, from trying to search for the electromagnetic signatures of these objects. Just with two detectors, the big yellow banana here that you can see is the area on the sky just from the LIGO detectors. When Virgo was added to it, so that area in the sky shrunk down to the green area. It actually ended up as the little purple shape here. But it shrunk down from 11,000 square degrees on the sky down to 60. So 60 square degrees is much more tractable if we're looking for perhaps an unexpected signature. So we were all quite pleased that last year that Virgo and LIGO had got to the point that they were supplying us, electromagnetic astronomers, with error boxes and regions of the order of 60 square degrees. And then we thought, well, we probably now are in the game of actually trying to detect something, or have a reasonable chance of trying to detect something. So that was August 14th last year. Then in August 17th, this is what LIGO discovered. So as I showed you, these are the 5 signals that they had previously detected, and this is the time that they're observable for. And as I said, these will last about around 0.15 to half a second in terms of the total time that the wave is detected over. So then in August last year, 17th of August last year at 12:41, they detected this signal. And so this one was a little bit different to the previous 5, given that it went on for, we will see this goes on for about 60 seconds. So a completely different signal detected. And so this is how when you think of that all they're measuring are 2 distances, and then what they can give us, as we'll see, is the masses of the two. They can tell us that a massive binary system has merged in the universe somewhere, that they can locate it on the sky, estimate the individual masses, and even estimate a distance to the galaxy just from those 2 measurements. It's pretty astounding what the information that they can get from that. So this is, again, the signal's still going here. So this is when they knew that this was something quite different, pretty obvious that it was something quite different to the binary black holes. So at 12:41 UT, this is the daylight diagram of the Earth. And so, of course, then LIGO thought, well, it's a binary, because it lasted so long, they were able to say, this is a binary neutron star system. This is the sky area, just to highlight which observatories might be available to observe. So this is what they put. This is the notice that they put out. That many astronomers across the world, I think there were over 100 or 150 groups that had signed these agreements with LIGO to search for electromagnetic signatures, but under an embargo with the experiment. So this is what they sent us out first of all at 12:41. The key thing here, so they released what's called a circular, which is written in more understandable text afterwards, but this is the first thing that popped into our email boxes. So they suggested this event had a false alarm, which is signal or false alarm rate of 1 per 3 million days, so quite significant. And the probability of being a neutron star is 1. And so those 2 numbers really came from the fact that it lasted 60 seconds, not 0.15, and the frequency of the detection. So immediately, I and every other electromagnetic astronomer who received this email just looked at those 2 numbers and said, so where in the sky is it, and can I observe with my telescope? So they also released a map at the time, so you can see sky map. So they released a map of the sky given the probability in which it was enclosed. However, just even before we all looked at the map, just 13 minutes later, we got another email saying, well, actually, Fermi and Integral have both detected a short gamma ray burst, gamma ray source, within 1.7 seconds of the timing of the LIGO Virgo source. And so this shows you the detection from both of those 2 satellites. So this is Fermi and Integral observing at a few hundred keV. These are the two bands of Fermi. So this is Fermi's background. This is seconds before the merger. So this is the LIGO Virgo time frequency map. That's the time of merger, and here's the gamma ray burst signal here. So then we got extremely excited that potentially this is the first detection in electromagnetic waves of a gravitational wave source. And as I'll show you, the map here from Fermi was roughly in the same part of the sky that LIGO Virgo detected. So when they analyzed the data, so they didn't know all of these numbers at the time, but this is how it turned out. This is the final paper that LIGO produced. But the first order, they estimated it was about a 1.5 solar mass and a 1.3 solar mass neutron star, depending on their assumption about the spins. But that was the estimates of the mass of the individual components that had merged to produce this 60-second signature. The other very important thing is that they released this distance quite early to us, and it didn't really change from the early detection. 40 megaparsecs is the distance to the host galaxy, with a pretty small error bar if you're looking for galaxies in this region. So that made it extremely interesting, given it's 40. That's a relatively close distance if you're looking for transient objects, supernova-like objects which might be of order of supernova luminosities or 1,000 times nova luminosities. And then they merged to give an object which is of order of like 2.7 or 2.8 solar masses. So what they gave us is a sky map, which you can see up here, and I'll show you a movie of how that sky map was constructed. But as they gave us the distance to the source and the sky area, which ended up as 28 square degrees, which is pretty small for us and many of the electromagnetic facilities. So we have telescopes now which are of order between a few square degrees up to 10 square degrees. So mapping out 28 square degrees within a few hours presents no great difficulty. But of course, with this such a small volume, if that's of order 60 megaparsecs, or the limit that LIGO thought we could go to, you could just find all the galaxies or all the catalog galaxies in that volume, and then pick out the individual galaxies and just pick them off one by one, even with a small 40 centimeter telescope with a few arc-minute field of view, could easily pick off all of the galaxies, all of the large galaxies in here, and there are about 40 or 50 galaxies of reasonable stellar mass within that volume enclosed by 28 square degrees and 60 megaparsecs. And so that's the route that many telescopes in Chile then took. So between 11 hours later, so between the time that this was announced at 12:41 UT, when most of the major observatories were in daylight, and 23:41 UT, which is when the first telescopes in Chile started observing this region. Let me show you this movie created by LIGO to highlight how they located the source and the overlap between the LIGO Virgo and Fermi. So Fermi gave this relatively coarse and large error region on the sky. You can triangulate, or they could triangulate Fermi and integral to produce this ring on the sky, which brought them down to this sky localization region. Then LIGO by itself, just the two US detectors, produced this broken ring on the sky, and a non-detection by Virgo really enclosed this really brought that down to the 30 square degrees. And so these are the, I think there are about 20 large galaxies here within this region, and also within the distance of 60 megaparsecs. And this one galaxy, NGC 4993, turned out to be the host of the neutron star merger, and the object is there. So it was detected. Actually, turned out to be extremely easy to detect it once that was known. Once that sky localization map had shrunk from thousands of square degrees down to 28 square degrees. In the first night in Chile, at 23:41, there were 8 telescopes that observed it during the first night. These are the first 6 that observed it. So this is the time observed after the gravitational wave detection. So the Swope telescope was the one to officially find it first, but they were all within minutes of each other and all independent discoveries. They'd all picked out NGC 4993 as a candidate because it's in the LIGO volume, it's in the sky area, of course. It's at roughly the right distance, and it's quite a large galaxy. So it was I think it was number 3 or 4 in the list. If you'd listed them by probability, just by this total stellar mass in the galaxies or total luminosities, this was number 3 or 4 in the list. So all of these galaxies, so Vista was more capable of looking at the larger sky region because of its field of view. So Neil Tanvir led the group here to detect it with Vista in the near infrared. Master and Decam are also wide field surveys that are capable of doing the whole region of 28 square degrees. The other 3 are small field of view telescopes that just picked out individual galaxies. And it turned out pretty easy then to certainly detect this transient. However, at the time, then just detecting the transient didn't prove it was it, of course. So this was one of the teams, the SWOPE team, managed to also get a spectrum on the first night of the object. And this is the spectrum that they got here. So it's very blue, featureless. There are a few bumps and wiggles, which are currently still unidentified. They're probably real, but not identified with any particular element. So they got this spectrum on the first night, and we were sharing all of this data at the time. All of the groups here announced that they had discovered it amongst this worldwide collaboration to try and confirm that this was indeed the source. And so the key thing was just what happened over the next few nights. So this is pretty hot black body temperature, 10,000, 11,000. Still could have been a CV, a cataclysmic variable in chance coincidence with the galaxy, or potentially a young supernova. But what happened over the next few nights convinced us this was actually it. So the next night we took a spectrum on ESO's NTT telescope as part of our PESTO program. And as soon as I saw the spectrum, so of course we were all staying up as late to look at the data as soon as we could from any facility that we could get. And as soon as I saw this, that it had gone from 10,000 square degrees in one night, and within 24 hours, it had cooled to 4,800. That's quite unprecedented for any known astrophysical transient. Given that in PESTO, we've looked at about 1,500 objects, classified at least 1,500 objects, that behavior was the most peculiar that any of us had seen. We didn't see any of the common elements. There's no hydrogen, no helium, no silicon, oxygen, magnesium, carbon that we typically see either in young supernovae or in CVs in our own galaxy or in any type of erupting or variable star. We saw these unusual absorption features here that are still not identified but are certainly real. But the fact that it had cooled and had this very unusual temperature evolution was the time I think we thought this must be the object. This must be related to the both the gravitational wave source and the gamma ray burst. So it turns out, this is on the left here. Here's a movie mostly made from Neil Tanvir's data from the VLT, and on the right is our light curve of the object over 10 days here in just plotting its luminosity that we've estimated over that period of time. So the unusual things about this, which are nicely illustrated in the movie, it starts out as a bright blue source, and you can see it's blue because of that spectrum was 10,000 degrees. It rapidly cools, and it turns red. So you can see it here as it turns very red and then disappears. So it drops off in luminosity really quickly and becomes red extremely quickly. So this actually matched, and it was about 1,000 times brighter than a nova in our galaxy. And that's where the term kilonova had been termed several years ago by Brian Metzger, who had predicted that neutron star mergers would produce such a signal. So here's another image of it here in the galaxy. I'm going to skip over that. So what can we expect from gravitational wave sources? Well, these neutron star mergers had been predicted for many years to produce an electromagnetic signature. Here's a simulation of hydrodynamic simulation of two neutron stars merging by Stefan Roswald. And so they had been predicted to produce a strong signature at optical and near-infrared wavelengths. And the reason for that is that in the periodic table, the elements up to the iron group, so hydrogen, helium, carbon, nitrogen, oxygen, the most common elements in the periodic table are all predicted to come from supernova explosions, and we've confirmed that over several decades. And up until last year, there was significant debate. There still is significant debate about what are the major producers of all of the chemical elements heavier than iron, because the difficulty, of course, is that the Coulomb barriers are too large to produce these in stars. before supernova explosion, and of course you can only reach iron. Stars will only evolve to produce an iron core. So there has to be some other mechanism that produces these elements. And the idea, and this goes back to work in the 1950s, is that capturing neutrons onto heavy seed elements can produce virtually all of those heavy elements heavier than iron. So for example, if you have an iron nucleus and you bombard that iron nucleus with neutrons, the neutrons are captured by the nucleus. It forms a very massive but unstable nucleus. Those decay, those beta decay, and the neutrons decay to protons. And then if you can absorb enough neutrons quickly, you can build up to the very heavy elements. So this is called the R process, and there's no secret about the R. It's just for rapid because you need a lot of neutrons very quickly. And this can potentially produce the very heavy elements that we know of in the periodic table, like gold, lead, platinum, iridium, osmium. These are the most. These are in the most abundant, very heavy elements. And there's also a group of lighter abundant heavy elements that this can produce as well. So this was predicted for has been predicted for a long time, but we've been concerned that we hadn't fully understood exactly what the astrophysical site for this actually happens. So this shows you the mass numbers of the elements in the periodic table versus their relative abundance. So everything up until iron, we assume, is produced mostly in supernova explosions. And then there are these three peaks here of these heavy elements, and these are the elements that we think are produced in this rapid process, which I say dates back to the work in the 50s by Burbage, Fowler and Hoyle and Cameron. And so I think now is the first time we're really confident we find at least one of these sites. Because the kilonova, of course, has to be powered by something. So this object, which is radiating from the ultraviolet right through the near-infrared becomes more important as time goes on, needs to be powered by something. So what we think is happening here is that we have radioactive material in the kilonova, that those heavy radioactive elements, those R process elements that are formed, decay through beta decay, alpha decay. They produce fission fragments as well. The very radioactive, the very unstable heavy elements produce fission fragments, which also decay to produce gamma rays. Neutrinos probably stream out, but these particles will power the source. And the key prediction for this, so of course it's reasonable to ask, so why do we believe that these are actually the R process radioactive elements that is producing the electromagnetic signature? And the reason is that for any individual element, it's obviously an exponential. If it's a radioactive element, then it's producing heat, so the rate of energy injection is an exponential. But several papers over the last couple of decades have suggested that if you have many radioactive isotopes, as you would have from the R process, is that if you add all of those up, you end up by approximating this to quite reasonable accuracy by a Power law. And that Power law is determined by this number beta. So all of this complexity in the production of many heavy elements, which are radioactive, which are all decaying, are effectively enclosed just in this one number. And the prediction from those nucleosynthetic calculations is that number should be somewhere between -1 and -1.3. So there have been, this slide just highlights some of the most recent work in determining which of that complex array of heavy elements might be the major contributors to the radioactive heating. And it turns out it's most likely iodine, gold, depending on what the neutron fraction is, but iodine, gold, tin, californium, perhaps copper and strontium as well, that those are the most likely, are the biggest contributions to the heating rate, but that this number minus beta always falls between -1 and -1.3. So the question is, does that match what we see? So it turns out it does. So from the data that we have, if you add up all of the luminosity that we saw over the first 15 days, it gets a little bit uncertain at 15 days because the thing is so faint and it's only detected in the near infrared. But if you look at the total luminosity of the object over a period of 15 days, so this is just the power output of the object, We can model that with a small amount of mass, only 0.05 solar masses of ejecta, so a total of a 1.5 solar mass neutron star plus 1.3 merged together, only 0.5 is ejected, and it needs to be ejected at about 0.2 to 0.3 the speed of light to give us this initial very high luminosity. And to power that source requires a powering term in these models of about a t to the minus 1.2. So we found this in our models early on, and virtually all of the other papers that did some quantitative modeling of the light curve also came up with an exponent is about minus 1.2. So I think this is the strongest evidence that the R process was formed in this, because we need a powering source, radioactivity, which produces a powering term with this exponent, matches the expectations pretty well. Of course, now what you want to ask is, so what exactly is the composition, and did we detect any gold or platinum, as we all said last year? So, and as you saw in the range of the elements in the periodic table, there are 3 peaks of the R process, from germanium and strontium right through to gold. Do we have a handle on what are the main elements that were produced, and is this the site of gold and platinum in the universe? So it is a little bit more complex. So we don't know the answer to that. I think it's almost certain that there is a mixture of the R process that has produced this luminosity. When you look at the spectra, which many of us have done since then, we still haven't been able to tie down individual elements. And the reason is that it is a complex blend. If the material is moving up to 0.3 C, there are a large number of atomic transitions that are likely active in the optical and near-infrared regime, so it's a horrible blend of all of those. And so we're still working to try and tie down which are the most likely elements that contribute to the features in the spectra that we see, and I'll show you a few of those. But there are also predictions that the kilonova is more complicated than just one component that was produced, as that you may have a blue component, what we call a blue component, which is composed of the lighter R process elements and has a fairly low opacity. I think it's almost certain that we do need this low opacity component with the light R process elements because the object was so blue so quickly. It's difficult to do that with just the heavy elements like platinum and gold. They have a much higher opacity. They will produce an emission that peaks in the near infrared, and it's difficult to get the early blue component with just that. But it's quite possible there are 2 components. So this is from Dan Casson's Nature paper submitted last year at the time that all of the papers were made public. And this is how he visualized it, where you potentially 2 components formed after the neutron star has, the 2 neutron stars have merged, and there's one, when we say potentially a long-lived neutron star, but that only needs to live for a few seconds. To irradiate the disk with neutrinos, that would reduce the neutron fraction, increase the electron fraction, and that would give us, that's potentially the main site of these light R process elements. If you look at the spectra, and these are just 2 examples, and people are still working on this quite intensively. The difficulty is, of course, the atomic data for all of these elements and finding the most reliable atomic data for these, plus also modeling it in a realistic way. So one possibility that we suggested was that these features that we saw early in the spectrum were cesium and tellurium. We're still not completely convinced that that is true. The other way to do it is try and combine the different components to model the blue component and the red component individually, which Dan Casson has done. So no one has been able to reproduce all of the spectra at every epoch perfectly and reproduce all of the features that you can see. The green is the black is the model data, and the green are the observational data. So the black data is not a bad, it's a qualitative fit to the overall spectral energy distribution, and this is combining an early blue component from the lighter R process with a heavier component, which is mostly, I think, dominated by the elements like neodymium, europium, and probably gold and platinum. But there's certainly no individual line we could identify as gold and platinum currently. But they are in this R process mixture of the heavy elements, and the nucleosynthetic yields would predict that if this is dominated by the heavy R process elements, then gold and platinum certainly have to play a role. So let me come to conclusions about what we saw. So this was, what we did detect were two merging neutron stars. LIGO Virgo estimated that they were about 1.3 and 1.5 solar masses that they produced. They therefore had to produce an object of 2.8 solar masses minus the 0.05 of ejector or so. So we don't know exactly if a massive stable neutron star was formed, or probably more likely that it collapsed to a black hole. All of the papers that did some modeling at the time last year and have done so since have all come to the consistent conclusion that you need about 0.03 to 0.05 solar masses of stuff ejected, and that needs to be powered by the radioactivity of the heavy R process elements. Exactly what the mix of the R process elements is in this in the kilonova is certainly not settled, and that will take a lot more effort on the modeling side, and also we hope more detections. The stuff needs to be ejected at least 0.2 C, perhaps up to 0.3 C, because within 11 hours we had an object. We went from merger of these two sources to something which was close to supernova luminosities. It's up at 10 to the 42 ergs per second. So just to get that early luminosity, the matter needed to be ejected at pretty high velocities, and up to about 0.2 C. So this is, there's huge promise next year when LIGO and Virgo start their third science run. This also has implications not just for the interesting, from my perspective, the interesting questions over the origin of the elements, and particularly the R process, the heavy elements in the periodic table, but it also has had implications for physics as a whole. The sort of trivial thing you might say is that, well, the gravitational waves and light arrived at the same time within 1.7 seconds, and so at 130 million, the distance of the galaxy is 130 million light years, so gravity travels at the speed of light. So for many cosmologists, this was extremely interesting. There are alternative theories to general relativity and plus dark energy and dark matter that explain the current content of the universe, and some of those are ruled out because to this we know that gravity now travels at the speed of light to within this accuracy, 5 times 10 to the minus 16. I didn't touch on it, but this is also a new way of measuring distances. So if you think back to those equations, if you measure the strain and you measure the frequency of the gravitational wave signal, that gives the masses of the objects, and the amplitude then is dependent on the distance to the source. So it's a completely new way of measuring distances in astronomy, which is not dependent on anything else. What that needs, of course, from the EM observers, actually we play a fairly simple role in that in that aspect, and not all the gravitational wave people want from us is the identification and the redshift of the host galaxy, and then they can do the other stuff. So it's an important thing to do, but I think we play sort of an important but minor role because that's dominated by the physics of GR and what you can extract from the gravitational waves signature. So there are many papers that have been produced since then trying to constrain the neutron star equation of state given the gravitational wave signature and the electromagnetic information, and I think there's a lot of promise in that in the future in constraining neutron star physics. This also indicates, of course, that we did have a gamma ray burst, and for many years it's been suggested that these short gamma ray bursts are from neutron star mergers. This pretty much confirms it, I think. There are 3 or 4, but there's one very good candidate for a short gamma ray burst, which was detected at about a redshift of 0.3, so much further here. So and this was done by Neil Tanvir and collaborators a few years ago, where there was a short gamma ray burst and then a faint red object detected in a galaxy, which is potentially quite similar to what we've seen here, but much further away and of course much fainter. So I think that does this. We're all reasonably certain that this is now confirming that most gamma ray bursts, short gamma ray bursts, come from merging neutron stars. And it confirms one of the sites of the production of the R process elements. There's open questions on the rates, whether or not merging neutron stars, if there are enough of them over the history of our galaxy to produce the abundance that we see of the heavy elements. There's also an issue that in very metal poor galaxies, we see the R process elements produced very quickly, which would not be consistent with the lifetimes of merging neutron stars. So it's certainly a site for producing the R process, but it may not be the only site. There may be other processes involved. But we hope to answer many of these questions and open up some of these very new possibilities next year. LIGO and Virgo start their next science run in February. I think virtually every telescope in the world now has got an approved proposal to follow up the sky localization regions that LIGO produces in the hope that we'll find objects like this. I'd be surprised if we quickly find one which is so close and has such great data, but I expect we will find more next year. Just to give you an idea of the rate, the estimated rates of merging neutron stars is uncertain by a factor of 10. So next year, our basic uncertainty is we don't know whether we'd have one of these per month or one of these per year. And that's what we hope to find out. Thank you.
Stephen, thank you very much indeed. That was an excellent talk. Open for questions, but can I ask you to wait for the other Stephen to reach you with the microphone first, because we're live streaming these talks and people just can't hear on the communication link. So there's one question over there.
Horace Regnart, thank you for a brilliant talk. Is it possible, given the ultra-high temperature, pressure, and energy density of a kilonova event, that ultra-transuranic elements may be created with ultra-short lifetimes? And if so, is there a chance we might be able to detect their fleeting presence?
So the short answer is I don't know. I think the answer to the first part is probably yes, but they would have such short lifetimes and their abundance would be subdominant in comparison to the elements that we know are now, although we don't know individual elements. I think the ones that are dominant in the nucleosynthetic trajectories their abundances are large enough that they would always dominate. So I don't think they would affect that T to the minus 1.2. And we're not accurate to to even 10% of that. So I think the answer is, even if they were produced, we would find it extremely difficult to isolate those, because we find it difficult to isolate even the elements that we are almost certain are there.
Of course, the key phrase would be islands of stability.
So down here, Stephen.
Mark Cropper at UCL. Is it now possible, Steve, to use every single short gamma ray burst as a marker by which we search for gravitational waves?
Yes, so that's been, so they've done that. So what they've gone back to do with LIGO is to, because both the gamma rays and LIGO Virgo give very good temporal information, but poor sky localization information, both of them. So they've gone back to look for sub-threshold signals temporally coincident with any of the gamma ray bursts, and there's no detection so far.
So you said at some point when you were doing the electromagnetic follow-up that if you looked at the galaxies,
yes,
the one that you chose would have been in the top of the list anyway. Now, why is that? Is it just the mass or something to do with the age, or
just the mass?
Just the mass.
Just
you're the
saying,
biggest chance of seeing something in this. Okay.
Exactly. They come from neutron stars. They come from massive stars. Pick the galaxies with the most stars. That's it.
for Live UCL. A great talk, Steve. About your third bullet points about the distances, it's obviously great that one could get Hubble constant from that binary neutron star, but nature is not so kind enough to produce electromagnetic radiation for binary black holes, so we don't know the redshift. However, there are attempts to do it statistically. So I'm just interested in your perspective on how competitive would the Hubble constant measurement be, especially in the light of tension between other measurements?
Yeah, so ideally we would like neutron star measurements, but I think we're going to be dominated by the black hole detections, probably about maybe an order of magnitude, certainly at least 5 to 1. So I think that's really interesting, an interesting idea where if you've got a small enough sky localization map, you measure all of the redshifts of the visible galaxies there, and each time you probabilistically, because you've got a redshift estimate for the black hole merger, probabilistically estimate which galaxy it came from. I think the estimates are of order that you need somewhere around 50 to 100 of those, I think, if I remember correctly, events measuring in that way to be competitive. I think it's extremely interesting and it should be done. I think measuring redshifts now is actually quite cheap to doing this. In terms of the time and telescopes, and the payback is enormous. So I think both that aspect for binary black holes plus the individual neutron star merger should both be done.
And we know that the H0 measurement from the single event is between the supernovae and the Planck measurement. So, yeah. Okay, Stephen, thank you so much for an excellent talk.